Hello everyone, and welcome to Python Programming Practice. In this episode, we're going to be tackling Leetcode number 15 called 3Sum. This is a medium difficulty problem, so it's probably going to take a decent bit of thinking to come up with a good solution. We're just going to start by looking at the description and the examples here. So given an array called nums of n integers, are there elements a, b, c in nums such that a plus b plus c equals 0. Find all unique triplets in the array that gives the sum 0. Notice that the solution set must not contain duplicate triplets. So I guess if we find a, b, and c that equals 0 more than once, we have to make sure we don't include that more than once in the solution. So they're going to give us an example here. There's an input array of numbers, -1, 0, 1, 2, -1, and 4. And the output here looks like two triplets were found. So -1, this -1 here, this -1 here, and 2. If you add all of those three numbers together, you get 0. So that is a valid triplet that adds to 0. And then there's one other one, -1 plus 0 plus 1 also adds up to 0. So that is a second triplet. And notice that although there are two -1s here, you could like swap the orders of those. That doesn't result in an additional triplet in the output because that would be the same three unique numbers in the triplet. So that's part of not duplicating them. We wouldn't want to include that. There's a second example. The input is an empty list and the output is an empty list, so that's just handling a non-valid input basically. And another example, nums is just a single number, so something where you can't have a valid triplet because there's not three things in there to even check. The output of that is also an empty list. So that suggests that basically if we're past an input list that isn't valid, so something that isn't like at least length 3, we should probably just check for that right away and return an empty list for that. So we have some constraints here. It looks like the length of the numbers array will be between 0 and 3000. So 3000 is a fairly large input array for this probably, if we have to do things on n squared or n cubed operations. So we're going to have to come up with something probably reasonably efficient past this. And the actual values of the input array have to be between -10 to the 5th and 10 to the 5th power, it looks like. So we don't have to deal with any super huge numbers, but we have to be able to deal with things that are on the order of 100,000 plus or minus. So that's good to know. The problem itself is not actually super complicated. It seems that the hard part is actually going to be just figuring out a way to do this that's not kind of a naive brute force solution. Let's pull over to the code editor here. The kind of obvious way to do this would just be to do a triple for loop where we're keeping track of the three different indices and basically just looping through and trying every single possible combination of sums and then just keeping track of them all and then finally return a list of all of the sums, taking out whatever the duplicates are. So we're actually going to start by coding up this brute force solution just to think a little bit harder about the problem, but then we'll go back and actually try to come up with a better solution that is more likely to pass the grader. But for an exercise, we'll do the brute force solution to start with. So we're given a list of numbers and we're going to have to return a list of all the triplets. So the first thing to do is create or initialize a list to hold the triplets we're going to return. I suppose we might also want to do that check for if the list isn't at least length 3, we just want to return the empty list right away. So if nums, or not just nums, if len nums is less than 3, we're just going to return an empty list right away. So that will be something we just keep there. And then we need to initialize this empty list. Now we just need to come up with our triple for loop. So for I in range, we want to start at the beginning of the list, and our triplets can't go, and we're going to go to almost the end of the list, but we don't have to check the last two things because those are going to be part of our other loops. So we'll go to len nums minus 2, and then within this loop for j in range, well, we start from the previous index point, so I plus 1 to len nums, this time minus 1. And then we'll say for k in range j plus 1, all the way to the end this time, len nums. Now within the inner triple for loop, we just have to check whether the numbers at this position add to 0. So if nums I plus nums j plus nums k equals 0, we want to append that to the triplets. Triplets dot append. Now, we have to be careful in that if we come up with two triplets that are going to be duplicates, but they're not in sorted order, it's going to be difficult for us to identify them and determine that. We'll have to either sort them later or sort them now. And to remove duplicates at the end, we're going to use a set operation, which requires passing in hashable objects. Lists are not hashable, so what we're going to want to do is sort these three numbers and then pass it into and save it as a tuple so that we can do that later. So we're going to append to our triplets a tuple of sorted these three numbers. So let's just copy those in and put commas there. So that has saved a tuple of the three numbers that added to equal 0. And that's all we need with the internal logic here. So at the end, we just have to return the list of unique items that we found, or unique triplets. So a list of the set, because we want to eliminate the duplicates of the triplets that we found. So as long as there's not any syntax errors or misspellings here, I'm going to run this code against the simple example that they give first and see what happens. So it did seem to pass on the simple example, so that's a good sign. I'm going to hit submit and see how it does on the overall submission. Now we're expecting this to probably be too slow to actually pass it. So the submission details here shows that the submission didn't pass because of status time limit exceeded. That's kind of what we expected because this is a pretty slow solution, but it means that the solution itself was probably working in terms of finding the right answer. It was just taking too long. And we can see that it did pass almost all of the test cases. So 315 out of 318, 3 of them it didn't pass probably just because it was taking too long. So now let's think about how we could go about coding up a solution that does better than n-cubed runtime. So for that, let's pull over to our whiteboard real quick and think about it. Now, I've written some numbers here, and you'll notice something about the numbers that's key to solving this problem in better than n-cubed runtime, and that is that the numbers are in sorted order. You'll remember that even when we did the n-cubed solution, we ended up sorting the triplets so that we could eliminate the duplicates. But for a problem like this, Sorting the whole input array before you start is a way to put some structure onto the numbers in the array, which can enable us to come up with a solution that potentially runs better than n-cubed runtime. Because when the numbers are in sorted order, we can be smarter about which ones we check for triplets. This allows us to avoid doing a lot of checks that we weren't able to avoid when we use the brute force solution. The advantage really of working with a sorted array for this problem is that when we're looking at a potential solution, say we're looking at -3, -1, and 2, since the array is sorted, it allows us to know which direction within the array we'd have to change any one of these points or numbers in order to work toward a solution that could actually be valid. For instance, if we add up these numbers, -3, -1, and 2, well, that result is -2. That's not big enough. We want to add up to 0. So that means we have to shift up something in order to get closer to 0. So that could mean we'd shift this up by 1 and check that number, or shift this up by 1 and check that number. That's the key insight that can allow us to solve this problem in sub n-cubed time. By sorting it first, we can know which direction to move these pointers in to get a solution that might work, instead of having no idea. When the array isn't sorted, we don't know that moving this to the right will actually only ever increase our number, because maybe we randomly had a 0 or a negative number in this direction. But after sorting it, we know that if we move anything to the right, it's only ever going to increase our sum. And if we ever move anything to the left, it's only ever going to decrease the sum. So this can allow us to come up with a solution that is sub n-cubed time. It will be an n-squared solution. So let's show how we can go about doing that. Basically, what's going to happen is we're going to have to loop through all of the numbers at least once. That is pretty much a given. And what we're going to do is basically do a single for loop where we fix our first number that we're looking at after sorting the array. So first we're going to sort the array, then we're going to loop through, and we're going to fix the first number. So this is going to be, for this iteration of the loop anyway, this is going to be our first number we're looking at. Then we want to find two other numbers that add to that to equal 0. And we want to use the fact that this is in sorted order to look for those numbers without checking every single combination of these numbers. We want to only have to do an order of n operations on these numbers here to find any pairs that add up to 0. So one way we can go about doing this is using two pointers or variables to store 2 points at the start of that subsequence after the one that we fixed, and at the end of that sequence after what we fixed. So basically what we're going to do is this is fixed, so we have a -3 here, and then our first pointer here is pointing at the value -1, so we add that in, and then our one at the end, so that's the biggest thing in our whole list, is a 5. So what we want to do is add those 3 things up and see what we get. So the sum of -3, -1, and 5 equals 1. That is bigger than 0, so that tells us the directions that we need to move things in order to get closer to 0. In this case, since the sum here is larger than 0, we want to move one of these pointers, either this one to the left or this one to the right, in a way that will potentially shift this to being equal to 0. If we move this one to the right, since we're in sorted order here, this can only increase our number. Since we're bigger than 0, we don't want to increase the number. We want to decrease the number, so maybe we get a sum that is going to be equal to 0. So in this case, we're not going to change this one. We would shift this back by 1. So we've looked at 5, that didn't work. So now we're going to check 2. And then we would just check the sum again. So now we're checking -3 plus -1 plus 2. Well, that's -2. So this time the sum is actually less than 0. So since the sum is less than 0 in this case, now we want to shift this pointer up 1, because we need to get something that's bigger. And so if we shift that up 1, well, that's -1 again, so we know that's not going to change anything because we already saw that. So we would shift it up again, and we'd have a 0 here. So then we'd have -3 plus 0 plus 2. Well, that's -1, but it's still less than 0. So we'd shift that up again, and now we have a 1 there. We had -3 plus 1 plus 2. That is actually 0. So at this point, we've found a valid triplet with this, and our original fixed value. So we'd store that, and now, once these two pointers have gotten right next to each other, we've gone through the entire subsequence here, and that means we've checked every possibility that could have added to this to equal 0. Even though we didn't check every single combination, the fact that we were able to do this kind of stepping inwards based on whether we were bigger or less than 0 essentially allows us to only check each of these things in here once instead of checking every single combination, which will basically let us cut the runtime down from n cubed to n squared. So I've erased a bunch of the marks that I've made, and now let's think about how we'd actually go about translating that logic we just talked about into code. Of course, we're going to start just by having our triplets empty list to save things into. We're going to need to start with some kind of outer for loop that fixes each of the first indices that we're dealing with. And then we're going to have to store those two pointers that are moving inward toward each other. So we're going to have to initialize a pointer for the lower point and the upper point. And then we're going to need some kind of inner loop where we check what this sum is. And depending on whether the sum is greater than 0, less than 0, or equal to 0, we'll do something different. So if the sum is equal to 0, we have to store it, and then we can just increment really either of the pointers up or down 1 if it's 0. So we could say if it's equal to 0, we'll just move the lower one up by 1. If the sum is greater than 0, then we would move the upper pointer down by 1. And if the sum is less than 0, we'll move the lower pointer up by 1. And eventually, as we go along, these pointers are going to keep moving toward each other. And so when they meet each other, we essentially want to stop the loop. So we could use a while loop to do this, basically saying that while the lower pointer is, I suppose, either not equal to or just less than the upper pointer, we'll keep doing the loop. But once the two pointers are the same or overlap, then we can break out, and then we would go on to the next outer loop where we're fixing this new starting point here, and then the inner loop would then only be dealing with that. So let's pull back to our code editor and see how we can go about coding this up. So we can leave our code here that's checking for length and initializing triplets because we're going to need to do that again. Now we're going to work on an O of n squared solution with sorting. So we're going to need to start by sorting the numbers because that was kind of a prerequisite for even trying to do that solution. So to do that, we're just going to take the nums list and set it equal to sorted nums list. Now we can write our outer for loop. That will look pretty similar to the one we used before. In fact, we can probably just take and copy that over because we're still going to want to not check those last two things. So let's copy the outer for loop from our brute force solution. And now we can write, well, actually, we need to initialize our two pointers. So the lower pointer wants to be equal to the lower point that we fixed plus 1, just to the right of that. And the upper pointer, we're just going to set to the last element in the whole list. So that's just going to be len nums minus 1. And now we can deal with our inner for loop. So when we were looking at the code, we said this is going to look something like while the lower pointer is less than the upper pointer, and we'll be either incrementing the lower pointer up and the upper pointer down throughout this loop so that eventually they will meet and be the same, and then it will break out of the loop. But while those are not the same, we first check the sum so that we can work with it and see if it's greater than, equal to, or less than 0. So the sum is our three numbers here. So nums I plus nums at the lower pointer plus nums at the upper pointer. So S is holding our sum now. If that sum is equal to 0, well, we need to store that because it means it's a valid triplet. So if S equals 0, we need to do something. We're going to say triplets dot append, and then we're just appending a tuple or whatever we want to. Tuple or list would probably work here, but we'll say a tuple because we might need to get rid of duplicates again with that list set business at the end of everything. So we'll store this inside a tuple of these three values. And we don't need to sort this tuple this time like we did with the brute force solution because we already pre-sorted everything before the outer loop. So we know that these three things are already going to be in sorted order. And now if they were equal, we can just increment the lower by 1 and move on. So the lower value, the lower pointer, plus equals 1. Now, if it's not equal to 0, we need to do something else. So L, if the sum was less than 0, if it was less than 0, well, then we need to make the sum bigger to try to get something that might be 0. So in that case, again, we need to increase the lower pointer because that is getting us further down into the array with bigger numbers because it's sorted. So plus equals 1. Else, if it's not less than 0 at this point, it means it was greater than 0. In that case, we need to try to make the sum smaller. So that means we're going to move that upper pointer to the left to try to find some smaller numbers to make that sum be 0. So in this case, we're going to decrement that pointer by 1, so minus equals 1. So this logic should take care of what we need to save the triplets. So now at the end, we just need to return the unique triplets. So let's come over here and say return list set of our triplets again. So that's actually the same as this. I'll copy it over because I think I misspelled triplets. So we don't need to delete our triple for loop solution since we're returning something above it. This just won't be run now. We're just kind of keeping it there because we did do it. So let's go ahead and run the code to make sure it doesn't throw an error just on the basic kind of problem. And it does pass that. So let's go ahead then and submit on the actual full problem. I'm going to zoom in a bit and pull over on that. So the answer was accepted here. It was a pretty slow solution relative to the other ones. So we can see that it passed with a runtime of 3,428 milliseconds, faster than only 9.11% of Python 3 submissions. So although it did work fast enough to pass the kind of check here, it wasn't particularly fast. And the memory usage seems pretty poor too, because it used 336 megabytes. That kind of seems like a lot. And it was worse than something like 95% of Python 3 submissions. So although this submission does pass, it's clearly not the best solution that could be made for this problem. So I've pulled back to the code editor here so that we can think about coming up with a way to make the solution be a little bit faster and perhaps more memory efficient too. So when you run into a situation like this where your code seems to be meeting the basic order speed requirement to pass something. For instance, in this case, we did get a working n-squared solution, which as far as we know, might be the best way to solve this problem. There might be other ways you can speed up your solution by avoiding doing various work and checks within your loops. So if we can think about some ways to reduce the amount of extra work we're doing, perhaps cut out some loops, then we might be able to come up with a solution that is going to be faster. Let's pull back to the whiteboard example and examine some different ways we might be able to make this solution run faster. One thing we can notice is that we're trying to come up with a sum that equals 0. And since our array is in sorted order, if the first point that we're fixing is already bigger than 0, we know that the sum itself can't be 0 because everything to the right of the point is going to be bigger than 0 also. So we're just going to end up with a sum that's quite large. That means that if this first point we're fixing is greater than 0, we don't even need to check anything because the sum is then going to be greater than 0 for sure. So let's say that this was our first point here. We don't need to check anything else because everything to the right of that is bigger than 0. So if this is our first point, we automatically know that we don't have to check anything else, and we'll just break out of the loop entirely and return whatever triplets we found so far. So basically, we can add in another bit of code that checks that first point, and as soon as it's bigger than 0, we can just break out and return. So let's go back into the code editor and do that really quick. So basically, within our first loop here, we can say if the value nums I is greater than 0, we'll just break out entirely and return. Now there are a couple other things that we can do actually to make this go even faster. So let's pull back to the whiteboard again. So in our first example, when we fixed -3, and these were our 2 pointers, we'll notice that when the first sum was too large, we had to move this pointer over 1. When we moved it over here, well, we have a -1 again. That's not going to change anything in terms of our sum. It's the same as what we just saw. So if after moving this pointer over, we have the same number that we were just looking at, we can just go ahead and increment it again and completely skip checking that because we know that the sum is just going to be the same thing as what we did before. And the same sort of logic applies to the outer for loop. When we eventually have the outer loop move to -1 as the fixed point, it will check all of the possible triplets for that, and then it will move here. Well, starting with the same number as the starting point that we did here doesn't add any new possibilities for triplets. So instead of using this starting point and doing all the work of checking triplets here, when we see that we've incremented this and the value here is the same as the one that we just checked, we can just skip that iteration as well and skip the outer for loop to the next iteration. So if we go back into the code and implement this skipping of checking the same number for the outer for loop and the lower pointer when it's incremented up by 1, that should also save some computation time. So let's pull back into the code editor and see how we can do that. First, we'll take care of the outer for loop. So if we see 2 of the same values in a row, basically, we want to skip an iteration. So if the number we're at now is equal to the number that we just saw, so nums I -1, we want to just skip this iteration and go to the next one. So that's continue. We're also going to want to actually put and we're not at the first iteration. So the index here should be greater than 0. Basically, if we don't put this in here, then nums -1 is going to be potentially checking an index before the beginning of the array. So now let's also change that lower pointer so that whenever we increment it up by 1, we also check to see whether that new number is the same as the one we just looked at. And if it is, we can increment it, keep incrementing it actually again as long as we keep seeing the same numbers. So let's go to that part of our code where we're incrementing lower. And we were actually incrementing lower in 2 different spots. So maybe we should change that so we only increment it in 1 spot. So that will mean we only have to do this other operation in 1 place. So let's take that away and say, we'll do this if to make that save, and then we'll just change this to another if, but we'll say equal to or less than, and then we only have to increment lower in 1 spot. So anytime we increment the lower, we want to check to see if the new one that we're getting is the same as the old one, the new value anyway. And if it is, we want to just increment it again. And actually, we want to keep incrementing it like that as long as it's the same. So we'll just run a little while loop here to do that. So we'll say while our new value here, our new nums lower, after we just incremented it, is equal to the old value that we just had. So now that's nums lower minus 1. Well, that is the case. We just want to increment lower by 1 again. So we'll just keep incrementing it until we don't have a duplicate value. Now, we do actually have to add one extra thing in here. With this while check here, it's possible that the array ends with just a whole bunch of numbers repeated in a row that are the same. And if that's the case and we run this while loop, we'll end up incrementing lower too much and basically run off the end of the list. So we have to make sure that we don't do that. One way we can do that is just make sure that the lower value is not ending up bigger than the upper value, because we know the upper value is kind of a stopgap against running off the end of the list. So and lower still has to be less than that upper pointer value. So after running this now, these extra 3 checks should remove some work that we have to do. We're breaking if we see an initial value bigger than 0. We are avoiding extra work on the outer for loop, and we're avoiding some extra work on the inner for loop. In fact, the way that this inner for loop operation is running, this is going to actually mean that we're not going to add any duplicate triplets into our list anymore because of the way this works. Basically, any time we're seeing something that was the same as before, we're just skipping over it. So the end result of that is actually going to be no duplicate triplets are ever added into the triplets list. So that means we don't even have to do this kind of list set business that we did before to get rid of those duplicates. We can just return the triplets without even having to do that. So let's rerun this to see if it works and that we didn't make any mistakes here. So I'm going to go ahead and click run code on the test example. Oops, equals less than 0. That's not right. It should be less than equals. So that is a minor error there, but that should be easy to fix. Oh, it looks like there's another thing to fix. Oops, it looks like we've run into another error here. Num I greater than 0. That should be nums, not num. So let's make that change. And we should be getting close to something that's working here. So there we go. It passed the basic submission. So let's submit that for the competition or the problem as well, and pull over and see how this one does in terms of runtime. So this solution did quite a bit better than the first one. We got a runtime of 800 milliseconds, faster than 75% of Python 3 submissions. So that's a pretty large improvement from the first solution that we made here. And in terms of memory usage, actually, we made a huge improvement because that first solution had something like 200 some megabytes of usage. It was a bottom 5% submission. Now the submission only used 17 megabytes, and it's in the top 96% in terms of memory. So by avoiding some of those loops and avoiding having to save extra triplets that we ended up removing later on with that set operation, by avoiding doing any of those extra appends, we actually saved quite a bit of memory because we weren't storing these duplicates and then retroactively removing them. We just avoided storing them at all in the first place. So I hope this explanation gave you some insight into how you can think about approaching a problem and also taking a solution that is okay, but thinking of ways that you could potentially go back and add some extra code to improve an okay solution, reduce the work that it does in different places, and come up with a solution that's pretty good. So thanks for watching, and keep coding.